Welcome back to the Explainer. Today, we're taking a really fascinating look under the hood of programming by exploring Java data types, specifically the primitive toolbox. Whenever we're writing code, we're constantly working with data, right? And that data absolutely has to be stored in variables. But here's the thing. You can't just toss any random piece of data into any variable. It just doesn't work that way. Variables need very specific, perfectly sized containers to store your data efficiently. So today, we're going to unpack exactly how that works and why it's absolutely crucial for writing great software. Let's get right into it.
Okay, let's dive into our roadmap for mastering these primitive data types. First, we'll open up the primitive toolbox, then we'll be sizing up integers, looking at the decimal dilemma, jumping into text and logic, and finally, avoiding common syntax errors.
So, part 1, the primitive toolbox, focusing on inbuilt data types.
So, what exactly is a primitive anyway? Well, in Java, when we talk about data types, there are really two broad categories. And we're focusing entirely on the first category today, which is the primitives. Now, as for that mysterious second category, we'll definitely explore that in a future explainer. But primitives, they're the simple, inbuilt data types provided by Java right out of the box. Think of them as your fundamental building blocks for numbers, decimals, individual characters, and your logic. Going back to our container analogy for a second, primitive types are basically like having access to a bunch of different sized storage boxes. If you need to store a single pair of shoes, you don't rent a massive industrial shipping crate, right? You just grab a shoebox. Primitives let you pick the exact right box for the data you're working with.
Moving on to section 2, sizing up integers. Let's talk whole numbers in Java.
When we're dealing with whole numbers, natural numbers and their negative counterparts, choosing the right integer type is entirely about being smart with your computer's memory. If you look at the progression here, it's pretty clear. If you're just storing a standard, everyday kind of number, int is your traditional go-to container. That takes up 4 bytes or 32 bits of memory. But hey, if you know for a fact your number is going to be small, you can use a byte or a short to actively save on memory. On the flip side, if you're tracking something absolutely massive, like, the distance between stars, you'd want to upgrade to that 8-byte long container. Now, you might be wondering, how do we actually know what fits inside that smallest container, the 1 byte? Well, it all comes down to a specific mathematical calculation based on the bits. And because it has to account for negative numbers too, the range actually doesn't start at 0. The math works out like this. It starts at -2 to the power of 7 and goes all the way up to +2 to the power of 7 minus 1. And when you actually do that math, you get a very specific range. -128 to +127. That is a really tight 256 number window. The absolutely crucial takeaway here is that if your value is exactly within this window, say you just want to store the number 5 or maybe 120, a byte is hands down your most memory-efficient choice. You're using the shoebox instead of the shipping crate.
All right, section 3, the decimal dilemma, pitting float against double.
So that covers our whole numbers, but what happens when we introduce a decimal point? Let me pose a quick question to you. If you just type a plain decimal number into Java, like 5.6, what type does Java automatically assume it is? Does it default to the float type or the double type? Just think about that for a second. Now, if you've programmed in older languages like C, you might have a guess, but remember, Java kind of does things its own way. Well, if you guessed double, you're absolutely correct. Java defaults right to double. Let's compare them. A float takes up 4 bytes of memory, which is great for saving space, but it has limited precision after the decimal point. A double, on the other hand, takes up a full 8 bytes. So why would Java favor the larger container by default? It's simple. Java wants to ensure maximum precision right out of the gate. When you're performing highly sensitive scientific calculations, you really need that long trail of exact numbers after the decimal. Double guarantees that high-fidelity accuracy for you.
Next up, section 4, text and logic. We're talking characters and booleans.
Now, shifting gears completely away from mathematics, what's really interesting about characters is how Java evolved past its predecessors. See, in older languages like C, a character was just 1 byte, utilizing the ASCII format. But the thing is, ASCII is mostly limited to English characters. The creators of Java stepped back and asked, hey, can we have all the characters in the world? And so they built Java to use a 2-byte Unicode system instead. This means it has a massive 16-bit range, allowing your code to natively support regional characters and symbols from languages literally all across the globe. It's a real game changer.
But when you actually go to write a character variable, which we call a char, there are some pretty strict rules you gotta follow. First off, you must use single quotes. Double quotes are strictly reserved for longer strings of text, not primitive characters. And remember, the char container holds exactly one character, period. It can be a letter like K, or even a digit acting as a character like the number 8, but it can only ever be one single keystroke. Next up in our toolbox is the boolean. You know, when we say a computer can think or make decisions, it's really just evaluating if something is true or false. Now, in some other programming languages, true and false are actually represented mathematically. They'll use a 1 for true and a 0 for false. Java says no way to that. Java booleans strictly and exclusively use the actual keywords true or false. There are no numeric equivalents here, which honestly makes your logical conditions incredibly clear and easy to read. All right, bringing us to Section 5, avoiding common syntax errors. Let's talk about keeping the compiler happy. With all these very specific containers we've talked about, it's surprisingly easy to make a mistake. And if you break Java's strict rules, the compiler will stop you dead in your tracks with a pretty notorious error message, possible lossy conversion. The crucial point here is understanding exactly why this happens. Let's say you take the number 129 and try to cram it into a byte variable. Well, as we just learned, a byte maxes out at 127, right? So the compiler flags it. Or if you try to put a default 8-byte double, like 5.8, into a 4-byte float variable, the compiler's going to stop you again. It's doing this to protect you from accidentally chopping off or losing your data during that conversion. It's actually a good thing. So to keep the compiler happy and avoid those annoying lossy conversion errors, you really just need to memorize a few golden syntax rules. First, if you specifically want to float, you've got to append a lowercase f to the number. Second, if you're using a massive long integer, append an L to the end of it. Third, always use single quotes for your chars. And finally, use the full keyword boolean. Our source actually shares a pretty funny, relatable anecdote about this. When you're switching between multiple programming languages all day long, it's incredibly easy to get your wires crossed and accidentally type the shorthand bool instead of the proper Java keyword boolean. And let me tell you, the Java compiler will not be amused by that.
Well, we have covered a lot of ground today, looking at the exact containers Java provides to store your data efficiently. But before we wrap up, I want to leave you with a bit of a provocative thought. Sure, saving 2 bytes by using a short instead of an int might not seem like a huge deal for a tiny, simple program, but how might choosing the exact right primitive data type impact the performance and memory of massive, global software systems that are processing billions of variables every single second? Thinking about the macro scale of memory architecture, that's the leap that takes you from just writing code to truly engineering software. Keep learning, keep experimenting with those variables, and we'll catch you in the next explainer.